All right, well, welcome to our October Artificial Intelligence for Clinicians, AI4C lecture series that's sponsored by the Mass General Brigham AI. And today we have another wonderful speaker, Dr. William Shu from University of California, Los Angeles, is going to talk about opportunities and challenges of using multimodal data to detect and diagnose cancers earlier. And as people are still logging in, just a few bits of information about the series. As you know, this is every second Thursday of the month, and we go September through May. We take the summer off. We have a great fall lineup. Last month, we had Adam Flanders from Thomas Jefferson and the RSNA board, and today we have Dr. Shu. We have Andrei Fedorov from Brigham, and then Safwan Halabi from Northwestern and Leary Children's Hospital. As always, you can view past recordings at the link there, and Carrie Ann has put that link into the chat if you are interested in seeing any of the past recordings. We do ask you to fill out the survey if you would. That link is also in the chat because this can help us improve the series and answer questions that you may have. You can also visit us online, and also on LinkedIn and see some of the activities that we provide through Twitter. So today, we are fortunate to have from the West Coast, Dr. William Shu, who received his Bachelor of Science from Johns Hopkins University and a PhD in Biomedical Engineering from the University of California at Los Angeles, UCLA. He's currently a professor of radiological sciences and also bioengineering at UCLA. He's a member of the Institute for Quantitative and Computational Biosciences and a member of the Johnson Comprehensive Cancer Center at UCLA. He's a biomedical informaticist, and he focuses on maximizing the utility of multimodal data, and that's what we're going to hear about today, to detect and treat cancers earlier. His lab harnesses artificial intelligence and machine learning techniques to integrate and transform multimodal data into actionable knowledge for clinical impact. He serves as principal investigator on multiple grants from the NIH, the National Institutes of Health, from the Agency for Healthcare Research on Quality, so AHRQ, and the V Foundation. He's a deputy editor of the journal Radiology Artificial Intelligence, the journal from the RSNA. He received a Basic Science Teaching Award from the Department of Radiological Sciences at UCLA, and he's a senior member of the IEEE, which is the Institute for Electrical and Electronic Engineers. And that's a very big organization and a wonderful honor to be a fellow of the IEEE. Today, he's going to talk to us about, again, opportunities and challenges of using multimodal data to detect and diagnose cancers earlier. So, Will, I'm going to stop sharing and give you the floor.
Great, fantastic. Well, thank you so much, Kathy, for the wonderful intro and for the opportunity to participate in this seminar series. It's really an honor for me to be part of really a distinguished group of speakers. Certainly looking forward to Andre's talk, certainly using the resources that he has really developed in terms of the image data commons. Some of this, will really enable some of the work that I'm talking about in terms of multimodal data. And so really today's talk is going to be in three parts. I'm going to try to introduce multimodal data and kind of the challenges as well as the opportunities for those of you who may not be too familiar with what's going on in this space. And then also highlight a few things that we're doing in my lab to specifically develop algorithms that utilize multimodal data. And a lot of my work is in cancer detection and diagnosis. And so a lot of the examples I will draw are either from lung cancer or breast cancer. And then finally, talk a little bit about how we are trying to translate AI in innovative ways to support clinical workflows. And so with that, I will go and kind of quickly introduce our group on the West Coast. So this is the UCLA Medical and Imaging Informatics group, of which my lab is one of several labs in this group. And so we are a group of faculty members in the Department of Radiology, but we are often jointly appointed with engineering school like bioengineering, with the goal of re-engineering healthcare by transforming data and knowledge to improve all lives. And so this is a group that has been around for a long time. It's been over 2 decades that it's been in existence. Started early on with PACS, and maybe like Kathy was actually a precursor member of the group in terms of her time at UCLA. But really, it's born out of the early work of PACS and then ultimately translated more into broader biomedical informatics and how we could actually essentially represent and integrate different types of data to improve clinical decision making. And so, if I were to sum up my research and kind of my research sort of goals, I would put it this way. So, here is on the left a sort of a patch of a CT scan. For some of you guys who are from radiology, you can recognize it's a chest CT scan with a blue circle circling pretty much a just the lung region, or a region in the lung, I should say. And the thing about this is that as we especially look at screening, and right now a lot of screening is primarily imaging based, like breast cancer screening, lung cancer screening. Patients who are at higher risk of lung cancer are recommended for annual screening. This was something that was proven through the National Lung Screening Trial and other trials showing that there is a lung mortality benefit in doing screening with CT. And what we see is that over time, some of these patients do develop some suspicious nodules. And really, the imaging provides a sort of a lens of what's going on biologically. And so, some of the things that we would like to understand is how do we interpret or understand the underlying biological better through the lens of imaging. And as many of you who have followed this field know that artificial intelligence and sort of this large amount of data that's available is really letting us mine the imaging data to an extent where now we get very specific and subtle features that you can kind of maybe a radiologist may not specifically call out, but are patterns that potentially can relate to specific underlying biological mechanisms. And so one of the things that I'm very interested in is understanding how do we use imaging to better understand things like some of you guys may be familiar with the hallmarks of cancer, which essentially describes some of the mutations and some of the programmatic changes that happen to cells that ultimately result in cancer. And some of the things that we want to be able to use this information is to really determine number one, is this suspicious nodule a cancer? Is it, if it's cancer, is it aggressive? And what kind of treatment should the patient receive or may respond to? And so just to summarize, I'm very interested in extracting biological insights and actionable information from multimodal data, which includes text from the electronic health record, as well as diagnostic imaging that we get in radiology, as well as pathology and digital pathology and molecular data, and to try to combine all of these different types of information to get a more complete picture of cancer. And the second one is really to then develop computational tools to help clinicians or even researchers try to interrogate this data and ultimately come up with more timely, accurate, and personalized management strategies. So let me start the talk by just kind of going over what is multimodal modeling. So on the left, you can see sort of these simple diagrammatic, and this is really not all encompassing of the different types of data. So as you can imagine, there's mHealth data, there's other types of more population-based data that I'm not representing here. So I'm just focused on clinical molecular imaging histology, and that's from the bias of data that I look at. But ultimately, one of the things that we need to do is first pre-process this data to extract meaningful features, right? So you need to process the images so that they become consistent, so that when you actually try to quantify things out of the images, that you're not just quantifying differences just purely because of differences in acquisition and reconstruction, but really because there's something biologically different. Same thing for other types of data, that there does need to be some pre-processing to prepare the data for analysis. Once you actually prepare the data, then there's the whole step of extracting relevant features and then fusing these features together. And so there's a lot of different methods to extract features, and I'll talk a little bit about that, as well as ways to fuse it. Some people just combine it all together. Some people actually have more sophisticated ways of adding different modalities. And so there's definitely a lot of research going in this space to optimize how we actually combine information. And finally, we have all of these different potential tasks. So you can apply it to improve our ability to identify patients and their risk of cancer, to inform screening strategies. Perhaps we, again, improve our ability to diagnose, look at aggressiveness and subtyping of disease, prognosis of patients, to understand whether we need to give more intensive types of treatments or not, and also specific treatments. And so these are all active areas that a huge number of research groups are trying to look at leveraging this type of multimodal data. And just to start with kind of the very basics about what happens. So, as I mentioned, there's different types of data, and some of the data comes structured, some of it is highly unstructured. And so others actually come from different institutions, and you would think that all of us using Epic or common sort of electronic health records may have very interoperable data. And the fact is that each institution has customized some of their implementations, and so going to a common data model like the OMOP partnership and so forth is actually an important step, right? And so we need to be able to collect data systematically because electronic health record data has a lot of missing information, has some, it was collected for a specific purpose like billing and legal that, may not include complete information that we need to really investigate a disease. And so how do we fill in the gaps by pulling information from other places, ingesting it into a common sort of data model in a common data location, like a data lake, where we can actually try to aggregate this, and then ultimately to transform this data in a standardized way. And so this picture was actually taken from a really nice review from a Stanford group that really kind of summarized some of these challenges of trying to train AI models and deploy it using the heterogeneous data sets that are out there. So that's one of the major steps, is really processing the data, cleaning it, and ultimately even trying to ensure consistency across the data to actually make it available for analysis. The next one is really then to represent the features and to ultimately fuse it. And so here are just a few examples, again, taken from another really nice review paper where you can actually extract, again, regions from diagnostic CTs or other types of medical images. And there are different ways of extracting features. So I will refer to some as radiomic features, as many of you know, which are predefined sort of algorithm, formulas that ultimately you can use to extract like texture features or shape or intensity. There's also pre-trained neural networks that you can use to extract higher order features or semantic features. And same thing with pathology. So just like how radiology, pathology also has different stains as well as pixel information that you can extract quantitative information from. And so there's a lot of different things and algorithms that you can use to actually extract useful information from digital pathology slides, with the added challenge that these are high resolution images. They're much more there are much more pixels in a digital pathology slide than radiology. And so in that sense, there's a challenge on the computational side of how to process these high resolution images. And then, of course, genomics, similarly, there's a lot of different types of information features that you can get from sequencing. And so I'm just going to list a few here. But ultimately, all of these features then are available for us to actually try to build models and to combine together. Since my research is primarily in radiology and medical images, so I just wanted to highlight specifically different ways. So there's really nice packages, some coming from MGB and others who are looking at how do we extract radiomic features, as well as pre-trained neural networks that we can use to extract features that are more complicated than just a texture feature. But ultimately, more recently, there's been a lot of interesting work, again, one of them coming out of Mass General, about pre-training these neural networks on very large data sets. And so here's one that they looked at a bunch of different lesions across different CT scans, really to build a foundation model for cancer imaging biomarkers. And these are, have been really valuable resources to the community, because for many of us who are trying to build these type of imaging biomarkers, having this kind of basis and ability to extract these type of features have been quite useful for our modeling. To give you a sense a little bit about the fusion and techniques for fusion, there's really two groups I would highlight here that people use to fuse data or features. One is what they call combination of data, which is combining features across sources to generate a single feature vector for classification. So you can have different sources here or different data types, and then ultimately either add them together or do some type of fusion where you're essentially combining the features to ultimately feed into a classifier that you would then train to do your task. There's also what's called the combination of interpretations, where instead of taking the data and the specific features from each data type, here you actually build independent classifiers on each of the data sources. So now you actually are essentially trying to interpret the information from the features and building essentially a model on top of that. And the predictions of the models, or interpretations of the models, ultimately gets fused into this fusion of interpretations. So many of you guys may recognize this as sort of like an ensembling approach. And so that's essentially what this is instead of trying to take all the individual features and combine it, here you're now taking a sort of a interpretation of the features and then combining it. And so in this slide, here's just a few things that are highlighted of different ways that you could actually do this. And so this is just taken from one of my a paper from one of my students where we're looking at combining radiomic and pathomic features. And so there are simple things that you could do, what's called early fusion or the combination of data, where we're essentially taking the features from each of these different modalities and concatenating it and feeding it into sort of a Cox regression model. There's other more sophisticated ways to actually combine the features, not just concatenating it, but actually learning sort of relationships between the features and finding the ones that have maximal correlation. There's also ways to actually interpret features, to actually feed it through a network to actually generate higher order features, and then doing some type of tensor product to actually build a model. And then we have the late fusion approach, which is essentially what I was saying in terms of the combination of interpretations, where we have these features, and then we ultimately build a model, and then we aggregate the predictions to actually come up with our final classification. And so when I talk about tasks, actually, in this slide, what I want to do is highlight a really interesting paper out of actually the Google Health Group, where they looked at, if we're applying AI, there's actually a bunch of myths and realities that we need to consider. And I think for this group, we probably are very familiar with some of these. But some of it is the fact that we just need a lot of data to train these algorithms. But of course, in reality, it's not just the quantity, but also the quality of the data. So ensuring that, again, we have complete data, we understand the biases of why the data was collected the way it was. These are things that contribute to building models that are trustworthy. In terms of the types of people who should be involved, it's not just technical experts, but really a multidisciplinary team between clinicians, maybe even biologists, radiologists, different individuals who participate in building an algorithm for a task. Um, we also need to know that not just that we have these laboratory experiments where we see that the AI does very well, but we really also need to do a lot of extensive validation. That includes external validation, right? Trying to make sure that the algorithm performs and generalizes across different cohorts. But also, we need to make sure that the type of workflow that we're applying the AI to, we mitigate any types of potential downfalls or pitfalls of using AI when we implement in the workflow. And so actually one of my examples later on in this talk will really try to hit on this issue. And so those are things that, as we think about using multimodal AI in practice, some of the things we need to keep in mind is that this is really a group effort, and one that will require a lot of data, but also high quality data, as well as a good amount of validation, as well as understanding how we can use these models effectively in the workflow. And so some of the open challenges I would just like to highlight are essentially, ensuring that the data integrity is there, that we have a bunch of different methods that we can use to fuse the data. Oftentimes with these different modalities, we need to normalize or ensure that they're consistent, that the models that we build are generalizable. So those are some of the things that I'd like to highlight. And actually the NIH has taken a lot of interest in this space. So recently they actually had a call for applications building ethically sourced multimodal AI models. This was actually earlier in May, and I believe that they will announce the awardees very soon. And then also, if you look at the link, and later on you can take a look at that, there's actually there was a request for information. So it looks like they are looking to potentially put new calls out in the future, hitting on multimodal AI and some of the topics that I listed on this slide. So certainly this is a very active area of research. So let me kind of ground some of these concepts specific examples drawn from my lab and some of the work that we're trying to do. Certainly, this is work in progress and things that we are trying to explore different methods for multimodal fusion. So I don't have a clear answer for you what is the most optimal approach to do things, but I would like to just share some of the experiences that we've had in trying to build these type of models. So let me start by motivating some of the reasons why we're looking at lung cancer. And I think lung cancer, especially the early detection and diagnosis of it, is very ripe for these type of multimodal models because, as many of us know, screening is not necessarily very optimal. A lot of times with CT scans, you will find a lot of suspicious nodules of which someone has to manage them. And so we need to figure out which ones need further workup, which ones can be safely just followed. And so all of this needs to happen right now through a radiologist, but ultimately, maybe an AI could help us sort of identify who's at the highest risk of lung cancer, right? So we have a lot of these clinical risk factors like smoking intensity, age, and whether or not it was for recently quit smoking, but those are not just the criteria that we should be using. And there are actually a lot of work, including Sybil, which is an algorithm that came out of, I believe, MGB, that basically is trying to use images to actually predict lung cancer risk accurately. Once you have these nodules are identified, then we have to characterize what the nodule is, perhaps give some sense to a radiologist, how suspicious should or how much care should be given to looking at this nodule. There's a lot of different algorithms that can now try to predict nodule malignancy based on the imaging and to try to determine whether or not, for example, a indeterminate pulmonary nodule that right now is a little uncertain, whether we can safely follow it rather than to immediately do something more intensive. Once we determine whether they're cancer or not, then we could also use imaging and other biomarkers to potentially help inform further treatment about neoadjuvant therapies, along with surgery later on. How do we sequence our treatment to best effectively address the cancer, but also to reduce the risk of recurrence? So these are things that I think are different places where AI has a lot of potential, and there's this really nice review paper that I was lucky to be part of to really explore this for the imaging space on indeterminate pulmonary nodules, and certainly would be a great resource for those of you guys who are interested in this space. And so what I would like to kind of highlight specifically is an area of high diagnostic uncertainty, which is indeterminate pulmonary nodules. So these are basically nodules that typically are less than 30 millimeters in diameter. We tend to use the range between 7 and 30 millimeters, because of the increased use of low-dose CT. Certainly, there's a lot of nodules that are now being identified that potentially fall in this range. And so today, based on sort of our risk stratification strategies, there is we can re-stratify these nodules between low risk and high risk, where high risk potentially would be a biopsy, low risk would be just imaging follow-up. But then we have this whole intermediate risk range where we're not quite sure, maybe it should be biopsied, but a lot of them could be followed. And so what we're hoping to do is build models that will help us identify, for the most part, many of these type of nodules that really are benign and can be followed up by imaging, versus a few of these cases that ultimately are more likely to be high risk. And so how do we, again, use the available data that we have collected clinically to try to improve our decision making on this? And so the first thing that I covered was the idea that we need a lot of good data. And so at UCLA, one of the things that we realized is that if we just purely relied on electronic health record data, it would just not be good enough. And so we wanted to basically create a shared resource to try to collect this data and collect it in a way that ultimately linked the clinical data with the imaging and pathology and other things that we may be collecting on these patients. And I encourage you guys to visit this website here. It's public. You can take a look and see not just in lung, but other domains where we're collecting this data. And would love to hear from you guys if you're interested in collaborating. So one of the things that we're doing specifically in lung is actually trying to bank blood and tissue with the goal that we can try to incorporate these biospecimens with the imaging to improve our ability to detect and diagnose cancers earlier. And so, with that, for these patients who are coming in, they get a low dose CT scan for the screening patients, or even for the non screening patients. Maybe they had some incidental diagnostic CT where they have an incidental nodule. And so, with that, we try to collect some self reported surveys, the imaging exams themselves. We consent them for blood and nasal specimens. And then, for some of these patients who are ultimately going through to biopsy, we also collect their biopsy scan as well as bank some of the tissue that may be from the biopsy. And then we follow these patients over time to try to get some information on diagnostic, both their treatment and outcomes. And so, one of the things that I just wanted to particularly highlight about this process is that we really wanted to track these findings over time because some of the limitations of existing data sets. So, let's even take the natural lung screening trial. The data set has annotations, it has images for many participants over multiple time points. But the challenge is that they did not uniquely identify these nodules or these findings over time and basically link them together. And so there are ways to try to combine it, but in our case, what we wanted to do up front was actually try to track these nodules as they were observed and link them over time. So we have a database that does that. We keep track of the relative amount of time between events. We also keep track of when specific specimens were collected from patients, with the whole goal of being able to essentially recreate a timeline and also a sort of a history for these nodules as we track them, with the goal to ultimately look at how potential temporal changes may affect, a probability of malignancy. And so, and I just highlighted that we identify the findings, we maintain the temporal ordering, and so, with this information, so we collected a lot of clinical information, we collected the radiologist interpretations, the imaging, and so forth. What we wanted to do was build models now to try to predict whether or not a nodule is likely to be malignant. And so, some of our early work in this area was really revolving around trying to combine the clinical textual data from the radiologist imaging. And so one of the things that we really wanted to do was figure out, well, for these models, because we knew very early on neural networks were black boxes, it's hard to build trust because the algorithm, it's hard to say what the algorithm is really interpreting. We wanted to try to mimic the radiologist interpretation process. And so for the radiologist, there's a lot of these types of semantic features, consistency, whether or not it's a certain size, the margin, location. These are things that what we call semantic features that the radiologists think about when they are interpreting the nodule. And so what we want to do is follow that same process where can we have the model intentionally interpret these semantic features, not as a way to ultimately get to the diagnosis, but really to explain the model and the deep features that it's learning. So our early work was basically devising at the time a multitask neural network. So basically what that means is that there's actually a sort of a shared layers where we're learning some of the basic features from the nodules. Then we have these multitask layers that basically try to represent different features. And so here what we were doing was trying to predict for each task different semantic features, right? So again, nodule consistency, size, shape, and other features. And then ultimately, instead of taking these tasks or these specific semantic features, we actually took some deep layer here and we fed it into the higher level task, which was whether or not this nodule is malignant. And so again, the goal is not to use the network to try to reduce the dimensionality of the problem, but really to just use these layers as a way to kind of gauge, what is the model learning in terms of the semantic features, but ultimately try to use the deep features to still predict whether or not the nodule is malignant. And so we did this very early on with the Lung Image Database Consortium dataset. And so this was convenient because it had a lot of nodule annotations, as well as a lot of these semantic features. Of course, as you think about it now, like a lot of the limitations of this work is also tied to the LIDC, where, number one, these were not pathology confirmed diagnoses. So when we say malignancy, it's really a radiologist suspicion, right? And so that was one big limitation. And the other one is that because these are not all low dose images, actually a very small part of it is low dose, it's not necessarily a model that could be used on a screening population, but it was really a proof of concept about the model. And what we found was is that when we architected the model in a way with the multitask learning, we actually saw comparable performance with just a 3D CNN or a convolutional neural network. And what that means is that actually sometimes you think, oh, if I architect the model a certain way to try to make it more explainable, then actually it may reduce my performance severely. And actually, that's not something that we found here. So we actually found that it was actually a pretty good performance in terms of that. Of course, given that this performance was evaluated on LIDC, so this is something that was not, I would say, reflective of a real world scenario. And if you actually look at the semantic features, you can see that, depending on the feature, some of it was actually quite good. Some of it, like sphericity, was interestingly bad. And so these are things that we were definitely interested in saying, well, it sounds like the model is learning a lot of these features from the images as it's learning about whether or not the nodule is malignant or not. But we wanted to really try to improve it to be more generalizable and ultimately adapt it to more real world scenarios like the data that we would see today. And so with that, so this work was originally published in 2019. More recently, we've kind of looked at some of the more sophisticated methods to try to do this. And so one of them, as many of you may be familiar with, is this idea of contrastive language image pre-training, which is something that actually came out of OpenAI. They did it to essentially train their vision models with a lot of textual data that was available as well. And so we wanted to also adapt that for this particular task since we had these images of the nodules, and we have these radiology reports and semantic features related to the nodule characteristics. And so we thought, well, because it's hard to get a large amount of nodule imaging data, we could actually try to use a text to help us not only explain what the model was doing, but also try to use it as a way to pre-train the model so that we don't have to actually use so much images if the model can learn the relationship between the two. And so that's essentially what we did with this type of clip model, and we trained it to do that. But as you can see, when we actually run the model, even though it's trained with the text, the end model is actually just using the images. And so the goal here is, again, to just purely base it off the imaging, extract the nodule information, predict whether it's malignant or benign, and then take out what the model thought the other semantic features are, again, as a way to explain things. And so we had to do a few things to really adapt. So one is that we had the NLST semantic features. These are all structured information, and if for those guys who are familiar with the CLIP model, they trained it on sentences, right? So they had like free text that they trained it on. So we actually had to go through this weird process of taking the semantic features that were annotated and ultimately transforming it into a textual information using Gemini to actually kind of mimic a radiology report. We could actually augment this with UCLA reports if we were to, try to, fine tune this with UCLA data. But with NLST, we had only structured information. And then same thing with LIDC, we had to map it to NLST. They had different features, so we actually had to reinterpret some of it and ultimately to do the same thing. So now we have the text we can train the clip model with, we have the imaging, and then we essentially pre-train the model that way. And then to kind of show you how our model now does compared to some other sort of state-of-the-art models. So we have Sybil. So I just want to note that Sybil is a little different where Sybil actually takes in any CT images. It doesn't need to be, something that has a nodule. It was trained on a huge number of NLST cases. But of course, with the nodules, they did use some annotations of nodules to try to help the model identify places where there would be suspicion. And, it actually does look at a lot of nodule-like features as part of its interpretation. Deep IPN is a model out of the Vanderbilt group that we collaborate, and also our own model. So again, our model was trained with a mixture of NLST and LIDC data. And so with that, just to kind of give you a sense of where we are in terms of performance, so here is a specific data set. So none of these models were trained on any of these evaluation data sets. So we have UCLA, where we had a very specific cohort of indeterminate pulmonary nodules. We also have public data sets like LungX and this Duke lung cancer screening data set. And you can kind of see what the enriched proportions are in terms of malignancy here, as well as what the Duke data set had. And you can see here that in terms of the models, you'll see that the performance will bounce around. So in this UCLA particular data set, performance was particularly bad overall across all the different models. Of course, I would say that they're highly comparable in terms of between Sybil and our model, but Sybil has a slightly better precision recall curve. And so these are things, what I would just say is that, looking at different metrics is helpful. I know in the original Sybil paper, a lot of the emphasis was on the area under the ROC curve. It is always helpful to look at other types of metrics that may be available to get a better sense of how the model is performing. Similarly, we have model performance on another external data set. So this actually data set was coming out of a challenge that the SPIA and AAPM put together back in, I think, 2015. And so this, interestingly, you can see that, model performance is a little better overall. And ours tended to be, on the 0.74. And one of the things that I would just note here is that actually, if you look at what the data set constitutes, there's kind of two parts to it. There's actually a lot of some non-contrast enhanced images where these models do very well, and that makes sense, right? Because these models were trained on NLST, LIDC. Most of them, if not all of those scans, are actually not contrast enhanced. And so, of course, when you add the contrast enhanced images, and of course, the models go down. So one of the things that we're actually particularly interested in is looking at the boundaries of these models, right? Because one of the open questions I've heard in different discussions about, for example, Sybil, is whether or not we could potentially apply Sybil not just in the screening context, but non-screening context, right? And so, they actually showed in their external validation in a cohort from Taiwan that non-smokers actually they had still very good performance in their cohorts in Taiwan. And so, actually, one of the big questions that we had was, well, if we expand it and use Sybil as a way to potentially look at other cohorts, will the performance maintain the same? And of course, we pushed it to the extreme. It didn't, hold up. But ultimately, finding that boundary to see, yeah, there's a model potentially could be used for even broader context than what it was trained on, could be an interesting investigation. And finally, we looked at the Duke lung cancer screening data, and you can see some of the performance here. And so I think what hopefully you're getting out of these kind of performance metrics are that, although our algorithm is not necessarily, and we bolded the top numbers, but actually, it's very close to it. Like for example, here it's I would say a lot of the performance of these models are very close together. And so really for us, it's really looking at number one, that the approach is actually, the fact that we're using both text and imaging is helpful because it helped us generalize our model a bit better than previous. And then also we're training with less data. And actually one of the points I wanted to make actually at the end is that our model is trained with a lot less data than Sybil and Deep IPN. So the fact that we're combining the text and imaging actually helps with the training process. And one of the other side benefits I'll just highlight is that just like our previous work with the multi-task learning model, we can actually expel or not expel, but basically output semantic features. And so here we have margin consistency and other things that are now updated to match what a radiologist potentially would report on. And so here you can actually see the performance of these type of labels being pretty good. And so the takeaways of this work is really that semantic features really we feel prevents the model from taking shortcut learning and provides or improves its ability to generalize. We thought that our approach actually is a really nice way to effectively train with smaller or limited data sets, which is a real world issue. And so we have used much less data than Sybil, although again, Sybil was trained on not just nodules, but really on a broad set of scans. We thought incorporating semantic features would help us achieve results that were comparable to the performance of these other models. And ultimately, we made this model more explainable by providing these type of semantic features. One other thing I'll just highlight here is that we are also looking at combining radiomic and pathomic markers, particularly to look at the sort of risk of lung recurrence, particularly in early stage, lung adenocarcinomas. And so this is just highlighting work that we're trying to extract radiomic features, pathomic features from different regions of the lung tissue that was resected, particularly looking at different subtypes, and ultimately feeding this into a progression-free survival prediction model. And so we did this in an LST, and so I'm not going to go into too much of the details here on how we selected the cases. And just to tie it back to my earlier discussion about how multimodal models are built, we then, essentially did some feature selection and feature fusion. In this particular case, we actually used very simple concatenation to try to combine it together. And you can see here that, just to highlight that while the performance still has room for improvement, and this is an area that we're still very actively working in, you can see that the combination of pathology alone versus radiology alone is really the combination that actually gets us, some value. And so this is, again, to highlight the benefit of trying to do this type of multimodal approaches. And we are actively looking at blood markers. So this is an active collaboration with one of our faculty members in pathology, Jasmine Zoe, who has a sort of a methylation-based tool to look at blood and look at whether there's cancer signatures as well as what the sort of the originating location of that tumor is. And so we wanted to combine it with the imaging to ultimately be able to do nodule malignancy, tissue of origin, as well as semantic features. And so that's something that stay tuned for some results there. So for the last part of the talk, I just want to also highlight some work that we're doing looking at the impacts of how AI would have on a workflow. And in this particular case, I'm going to talk about breast cancer screening. So I know at some institutions, there's been very specific efforts to try to set up what we call same-day clinics for breast screening, where women who come in for a mammogram can actually get a diagnostic mammogram and potentially a biopsy on the same day. And so I think in literature, there's definitely been a lot reported. I believe MGB actually has one through Connie Lehman and others who've really tried to pioneer this. And for us at UCLA, we are also a very high volume academic medical center with a very, I should say, high volume breast screening clinic. And so one of the things that we wanted to do was see what were these type of breast AI algorithms that look at screening mammograms, that it would allow us to actually improve our workflows and speed things up so that we're not reading these mammograms offline, meaning like in batch later in the day, but ultimately while the patient is still at the clinic so that we can potentially offer them a diagnostic exam if needed. And so for those of you who are familiar with the breast screening process, we have the mammogram that is essentially read later on by a radiologist. Typically, it's as they have available time, but it's definitely not usually when the patient is still at the center. And so, of course, if it's negative, nothing really happens. But if it's a category 0 or something that is suspicious, they patient gets notified and they get called back for a diagnostic exam. And so, of course, there's a certain percentage. So at UCLA, that can range between 7 and 16%. And ultimately, that leads to this delay of care where there could be some anxiety. And that's one of the big motivators for trying to essentially turn it same day. Although you can also imagine access is an issue where if for women who, screening center is very far, coming back a second time is not very convenient and also can lead to loss of follow-up care. And so here, what we're trying to do is do all of this in the same day where the AI ultimately becomes a first pass reader and ultimately routes flagged exams that are highly suspicious to a radiologist to confirm whether or not a recall is necessary, and then ultimately to provide that diagnostic exam on the same while the patient is still at the clinic. And so the hope is to essentially do this and benefit, right? Like to hopefully see increased patient satisfaction and less delay in care. But ultimately, we know this could also potentially impact the workflow. As you know, this is again a high volume environment. So this will potentially have impacts on patient volume, length of stay for the patient, as well as the waiting times. And so what we wanted to do was actually, before we try to just dive deep into it, to actually do a simulation and try to set up a way for us to quantify what the potential impacts could be. And so here we collaborate with some of our implementation scientists at UCLA to really think about how do we develop a way to ask what if questions about real world scenarios where we can simulate the use of the AI as well as this whole workflow of trying to fit in a diagnostic exam to the existing breast screening clinic. And so we used a discrete event simulation for this. And then we essentially tried to model our workflows and see whether or not the simulation allowed us to, number one, recreate the types of volumes and things that we see in practice. And then number two, to then modify that workflow to add in the AI as well as the same day diagnostic exam to see its impact. And so here's just a example of this discrete event simulation model. I don't have time to go into all the details of this specific diagram. It's all to say that there were some assumptions that were made. We basically did parameterize it based on data, historical data that we had of the screening center, as well as we modeled the workflow based on one of the screening centers that we have at UCLA. Here is the modified workflow where we now introduce the AI, as you can see here. And then also as part of the AI introduction, we then also provide some simulation of the variation of potential recalls that the AI would make. So this is tied to some performance of the AI algorithm. And then ultimately, with combination with the radiologist interpreting it, we then have the workflow to actually look at how often a diagnostic imaging exam is performed. And so with that, the first thing we did was try to verify, does our simulation model actually, if we were to run, let's say 1,000 simulated patients through the system and the model, whether it would get us to the numbers that we actually see in practice. And in fact, it does. So we do see like a 3-day scheduling data, that kind of matches up with the model. So that was good and encouraging. And so then we wanted to say, okay, based on that, what impact does patient volume, length of stay, and waiting time have if we were to introduce this revised workflow? And if we were to then mitigate some of these changes by introducing other resources, right? So, like, for example, adding more equipment, adding another radiologist or a technologist to kind of help with the bottleneck that may occur at the time of diagnostic exam. These are things that we wanted to try to see what would be the impact of that. And so with that, we played around with the model. We basically tuned it or essentially did some sensitivity analysis of different parameters. And what we find is that introducing, the same day workflow, particularly trying to fit in extra diagnostic exams, clearly it will impact the workflow, right? So in terms of if we didn't do anything, then of course our patient capacity would have to decrease because extra exams for a subset of these patients, the waiting time will increase and the length of time or length of stay will also increase. And you can see there's some variation about how how much effect that would have on each of these. But the helpful thing that we saw was through these simulations, we can actually see what are, again, some what if scenarios where we can say, oh, if we added yet another mammo unit so that we can try to, stage patients better so that patients who are already scheduled for the diagnostic exam are not affected by these additional, add-on exams. So those are things that we played around with and saw that there are definitely some ways to mitigate some of the potential issues that we see in the workflow. And also one thing that we wanted to also look at is AI, because many of us, while we would like to think that AI will help and improve everything, in fact, AI can also make things worse. And as you know, with AI, especially with the early generation of CAD in breast screening, there is a lot of concerns about whether or not AI will, add more false positives than really help. And so we modeled that, and so we wanted to also see how that would actually impact the workflow and try to estimate how much time the radiologist would actually need to add to their day, essentially going through these AI flagged exams. And so these are things that we're certainly considering. And so we're not yet implementing the same day yet. We actually have an AHRQ grant that is looking at this actively, and we've moved into the phase of trying to do a pilot. And so that's helping hopefully in the next year. But ultimately, my hope about what I'm presenting today is really some of the simulated analysis that I thought provided a lot of useful insights about how this AI-aided same-day diagnostic workup could unfold. And so really, again, to help us plan out some of these issues that may occur, as well as to mitigate them. And so with that, I'm just going to conclude with a few thoughts about multimodal and AI in general. So the first one is that, I think especially in the cancer detection and diagnosis space, there's just a lot of things going on and a lot of exciting things with blood-based tests, biospecimens that may be available, urine for some cancers, tissue, where we could really do a good job in combining the blood, the imaging, as well as other things to, again, understand the biology and the biological evolution of tumors as they go through time, and as they respond to different therapies. And so the goal with multimodal AI is that we can get a better understanding of the patient's unique evolution and their cancer makeup to ultimately do better targeted and more precise targeting of therapies for these individuals. And so with that, imaging is a very versatile tool that allows us to do this type of in vivo quantitative characterization of the tissue microenvironment. There's a lot of developments in this space, and certainly a lot of great work coming from all the institutions that are represented on this call. I think that addressing the barriers to clinical translation will be critical in terms of getting cohorts that have high quality data that can be linked to clinical outcomes. You know, trying to address some of these data harmonization techniques. So one of the projects that is in my lab is really on harmonizing CT images so that quantitative analysis is comparable. Didn't have a chance to talk about it, but happy to chat about it later on. And also really understanding the potential impact of these type of models and multimodal models on clinical workflows. And so some of the open challenges I see as things that we need to really help build out or further develop are the fact that, as we translate these models, we're going to have missingness, right? There could be a missing modality or missing information. And so how do we get models to be better at accommodating those type of missing information? Also being able to address inherent biases in data collection and potential imbalances, particularly in cancer screening, where as you can see from some of my earlier slides, there's a large imbalance between cancers and non-cancers. And so how do we address that in our models? Open sharing of multimodal data. And so I thought Sybil is a great example of this, where they release the data, the model, it's out there, anyone can run it. And there's been a lot of people who've tried it. And I think it's been really good healthy for the community to openly run these models. And my hope is that our models that we talk about today will also be shared as well. And then finally, the opportunities, really trying to develop these type of point of care liquid biopsy technologies that complement imaging to ultimately do better job at, again, detecting and diagnosing cancers earlier. So with that, I'd like to just thank my lab as well as collaborators who've really kind of enriched sort of my understanding of this space, as well as helped me stay motivated in terms of all of the things that we're doing in our multimodal modeling. And with that, I will end here and just open up to any discussion or questions. Thanks so much.
Wow, fantastic, Dr. Chu. That was a terrific tour there. Really fascinating how I think really knowledge discovery has changed significantly in healthcare and how these tools can be used. And you really brought it all the way through to, well, so how are we really going to impact clinical care and what that might look like? Very, very interesting. And I wanted to ask you about, I know you have this infrastructure for the integrated
Yep.
diagnostic
Mhm.
that includes so many wonderful things, and you shared the link there. Could you describe that a little bit more, and how was
Mhm.
that conceived? Was that
Yeah.
something that happened from institutional basis? Did
Yeah.
you, start this? Was it within radiology and you brought in other things? How did that happen?
Yeah, that's a great question, and I have to give a lot of credit to others. So it really originated with, I think it was for a long time. So this program has been in existence for over 10 years, and it's essentially, I would give the credit to the brainchild of our chair, Dieter Ensman, who really thought at the time, he was very interested in looking at imaging, not as at the time just looking at image impressions, but really trying to make something actionable out of our radiology reports. And so he very early reached out to pathology and said, you know what, we really need to be working together to better understand what we see in the images and correlate with the pathology. And really through that partnership, they built this resource. And so we started in prostate. And one of the things that we originally did in prostate was, there was this very unique workflow where, and we borrowed this actually, it didn't originate at UCLA, but we operationalized it there, where we took like a prostate MR, we segmented the prostate, and when the patient came back for their radical prostatectomy, we actually would generate a patient-specific 3D mold. The prostate comes out, it goes into this mold. The mold is basically two things. One is it actually helps the pathologist cut the prostate to do the slides to prepare the whole mounts. And the second one is the slide that the slits actually correspond with key images on the MR. So the premise of that is really that we would be able to spatially correlate and try to mitigate any kind of spatial variation between the tissue and the imaging to ultimately do sort of this cross, correlation type of analysis. And so that was where we had our humble beginnings. That in itself is another resource that happy to again talk with others about who's interested in leveraging this type of data. But of course, other sites like NIH, I think Stanford may have a little bit, but other institutions have definitely built up their own data there. For lung, I would say it was really led by Denny Aberle. Some of you may recognize her as the one of the PI for the National Lung Screening Trial, and so she really, from that trial, very early on said we need to collect this data, take care of some of the limitations of an NLST, but ultimately to link it to the biospecimens. And so a lot of the specimens that we collect as part of the lung program within the integrated diagnostic shared resource is actually through her vision. So hopefully that kind of addressed a little bit of your question.
Yeah, no, fantastic. Thank you. That was great. And I did see some of the results of that infrastructure of that resource when I visited, which was really very, very impressive. I wanted to pose a question. You talked a little bit about some of the limitations, or maybe not limitations, but areas to think about and to go after in future. And along those, talked about the liquid biopsy and
Yes.
so on. And as I'm thinking about opportunistic screening. So
Yes.
getting someone to come for screening for lung cancer, we know there are certain demographic groups that maybe don't get screened as often as they should. How do we improve that? Or can we be using materials that we already have in our electronic medical record, such as all the multimodal data that you have, or maybe even a CT that was done and
Yes.
maybe it wasn't, there was nothing visible to the human eye vis-a-vis lung cancer yet, but
Yeah.
maybe there are features that your model could detect. What do you think about that? And certainly for breast imaging as well.
Yes.
Are there ways that we can use these newer knowledge discovery technologies to perhaps to find folks earlier on in their journey towards cancer?
Absolutely. I think that's a great question and definitely is one that is a huge amount of active area research. So there's a lot of interesting work, and I think Sybil definitely started this type of conversation where because they demonstrate such high performance on screening exams that ultimately, these images really didn't have anything suspicious, right? What I would consider like subclinical, right? Like there could be something, but the radiologist would never have called it, and they showed very accurate risk prediction based on those images alone. I think opened up a lot of opportunities. And they also did this, the same group did this in breast cancer where they have a Mirai model as well. And I definitely do believe that, opportunistic screening is definitely a very hot area where we could leverage because a lot of people get imaging for various reasons. And so there's different strategies around this. Certainly, there's a lot of work in building algorithms that will detect findings that are outside the typical scope of focus for why the imaging was originally acquired. And so, for example, one of the things that I'm doing with one of our thoracic radiologists is, yeah, looking at how a model like Sybil could generalize, right? In terms of, maybe not a specific low dose screening exam, but how do we make it work better for diagnostic exams, right? Because again, here you could potentially use a model like that to risk stratify patients and maybe even identify patients who would benefit from screening but are not screening eligible. And so these are things that we're trying to investigate a little further. And then also, as we look at blood tests, for example, now those, we get on a routine basis. Imaging is a little less so, right? Because, not all of us are getting whole body MRs and we probably shouldn't be necessarily. And so
Hopefully not.
yeah, exactly. And so these are things that I think a blood test, which is, could be very sensitive, could be paired with imaging technology or other types of devices, also ultimately to help us, identify patients again at either increased risk or already have some signs of early cancer. The final thing I would just say about this is that, our interactions with patients are somewhat limited in the sense that, it right now a lot relies on them coming to the health system and being part of the health system. And some of the really interesting work that I've seen outside of it is, wearable sensors and being able to like do things at home with your smartwatch, or even just something that is easy to do at home to do, again, a test or some measurement outside of the clinical environment, where you can kind of fill in some of these gaps that we talk about in terms of, long periods of time, even a year, right, where patient is not imaged. And so there's a lot of things that could be happening in that period. So those are some of the initial thoughts.
No, fantastic. And Allison Chang here has asked specifically around the Sybil model. Just to clarify, is your model focusing only on the nodule, or specifically on the nodule, not the entire CT volume
Yeah.
like Sybil is doing? And
Yeah.
is a radiologist required for identifying the nodule of interest?
Yeah, that's great. Yes, thank you for asking that clarification. So we actually are, the model that I was showing, the performance are based on essentially the nodule has been detected, right? So these are focused on the nodule. It's not just taking in the whole CT and finding the nodule. So in that sense, Sybil is certainly, much more kind of capable to be able to do that. Although they're not necessarily looking for the nodule, right? They're kind of looking at things that may be nodule-like because they trained on it, and that likely contributes to its risk. But they don't say that their model is a nodule detector either, right? So for us, we rely on the nodule, but we do have work in looking at nodule detection. So that's something that is an active area of research of ours. We didn't talk about it today, but one of the things that I found for that work is how important it is, again, to have sort of scans that are consistent, because a lot of times these false positives that come up in nodule detection is a lot to do with varying noise and other things that actually make things either look more like a nodule when they're not, or maybe even obscure nodules like part solid nodules. So these are things that we're certainly working through. And I know there's a lot of literature that kind of seems like, the nodule detection part is a solved problem. I would argue there's a lot of great algorithms out there, but they're not very consistent. And so how do we make it more generalizable and robust?
Fantastic. Well, thank you for that. And I want to be respectful of everyone's time. And we can understand why you won the teaching award. So that was a wonderful presentation. And we thank you very much. Will, thank you so much for a wonderful talk. Thank
Well,
you,
thank you so
everyone.
much, Kathy.
We'll see you next month.